All right, so I'm going to look at some free response questions. There's 6 free response questions. Each of them's worth 9 points, and you're allotted about 15 minutes a problem. The first 2 you're allowed to use a calculator on, and the last 4 you are not. And for the most part, there are certain types of free response problems that you're pretty much guaranteed to see. So I'm going to go over a couple of those types. I'm going to go over one type right now. So this is from last year's test. This was problem number 1. So it's on the calculator portion. And this is a pretty typical type of question. You're likely to see one like this. This is reasoning from tabular data. So basically it's data presented in a table and you have to answer questions about it. So in this one it says the temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function W, where W of t is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature is 55. The water is heated for 30 minutes beginning at time t equals 0. Values of W of t at selected times t for the first 20 minutes are given in the table above. A lot of the information that they just told you in written form you could have gotten from the table, but they're just clarifying. So part A says, use the data in the table to estimate W prime of 12, show the computations that lead to your answer, and using correct units, interpret the meaning in the context of the problem. All right, so W prime of 12, that's the derivative of W when t is 12. Derivatives tell us rate of change. So this is telling us how the temperature of the water is changing at 12 minutes into the heating of the water. So this is going to be, I'm not sure where to write this. Let's see. I can find a better color to write with since I have to write on this gray over here. So on part A, W prime of 12 is the rate of change of the temperature when t is 12 minutes. And we'll talk about what the units will be in just a second. No, rate of, let's try this again. W prime of 12 is the rate of change, not rate of the temperature, rate of change of the temperature when t is 12. Okay, now when you're trying to find a derivative or a rate of change from a table, you can't actually use a derivative because you don't have an equation that allows you to find the derivative. So you have to estimate it, and when we estimate a derivative, we use the slope formula. So we're going to use the slope formula. 12 is actually not one of the times on the table, so we're going to use the 2 times that are closest. And so we're going to do y2 minus y1 over x2 minus x1. And if I type that into my calculator, I can find a calculator that's not dead. Okay, let's see, then I would have 1.017. And the units would be degrees Fahrenheit per minute, because these units that I have on the top of my slope formula are degrees Fahrenheit. These that I have on the bottom are minutes, so this ends up being degrees Fahrenheit per minute. All right, so that's part A. All right, part B, use the data in the table to evaluate the integral from 0 to 20 of W prime of t dt. Using correct units, interpret the meaning of that in the context of the problem. Okay, so on part B, we're integrating the derivative of W. So when you integrate a derivative, you're canceling out the derivative. Those 2 operations undo each other. So if I integrate W prime of t, I get W of t. And then I have my bounds from 0 to 20. So after you integrate, you plug the top bound in minus the bottom bound. These 2 values come from the table. W of 20 is 71. W of 0 is 55. So this would be 16, and this is degrees Fahrenheit, because 71 and 55 are measured in degrees Fahrenheit. This represents the total change in the temperature over the 20 minutes. We just integrated the rate of change of the temperature. When you integrate a rate of change, you get the total amount of change. In this case, it would be over the 20 minutes. All right, so for 0 to 20, the average temperature of the water is 1/20th from 0 to 20 W of T dt. That's the average value formula. Use a left Riemann sum with the 4 subintervals indicated by the data in the table to approximate that average value. And is it an overestimate or underestimate of the average temperature of the water over these 20 minutes? Okay, so I'm going to erase these two. You can rewind the video if you need to see those again, but I'm out of room here. So I'm going to be doing 1/20th. Let's see here. Let's scroll down a little bit to get myself some room to write. All right, so I'm going to have 1/20th, and then I'm doing a left sum to approximate my integral. So, and I'm using these 4 subintervals. So my first rectangle will have a width of 4 and a height of 55. I use the height on the left for a left sum. My next one will have a width of 5 and a height of 57.1. My next one will have a width of 6 and a height of 61.8. And then my last one will have a width of 5 and a height of 67.9. So if I type this in my calculator, 1/20th of 4 times 55 plus 5 times 57.1 plus 6 times 61.8 plus 5 times 67.9, 60.79. This is degrees Fahrenheit. All right, so is this an overestimate or underestimate? Well, if you notice, this was a strictly increasing function, which means as you move from left to right, the heights are getting bigger, right? Strictly increasing. So anytime you use a left sum to approximate area under an increasing curve, you're going to have an underestimate. So this is an underestimate. A left sum underestimates on an increasing function. And just to kind of track where we are points-wise, I didn't really talk about that, but the first part A, where we found the W prime of 12, that was worth 2 points. 1 point for our estimate, our actual answer, and then a point for telling what that meant and using the correct units. And then part B was also 2 points. We got 1 point for finding that value, and then a point for saying that it was the total change in temperature. This part that we just did, part C, this was 3 points. It's a point for this part in here. It was a point for the answer, and it was a point for explaining that it was an underestimate. Okay, part D, hold on just a second. All right, sorry about that. I wanted to get my calculator set up. Okay, so on part D, we're now looking at an interval that was not contained in our table up here. This is saying the water's heated, we know from the problem, for 30 minutes, and these are just temperatures over the first 20 minutes. So now for the next 5 minutes, from 20 to 25, the function that models the water temperature has a first derivative given by this equation. Based on the model, what's the temperature of the water at time t equals 25? All right, so we know that at the start of the interval, we're at 71 degrees. And then we talked about on part B that if you know the rate of change of something, you can figure out the total change by integrating. So if I integrate this rate of change of the temperature from 20 to 25, I'll get the total change over that time period, and if I add those two things together, then I can get what the temperature is. So this is the starting temperature at the start of the interval 20 to 25. I got that from the table. And then this represents the total change in the temperature over those 5 minutes. So you can put this in your calculator. What we'll do, I got to do this, hold on. What we will do is go to our calculator, and I'm going to insert calculator page into this document. Actually, no. I'm going to go home and just do the scratch pad. Okay, so what I'm going to do is I'm going to do 71, because that's my starting temperature, plus menu, calculus, numerical integral. The integral from 20 to 25. And then I'm going to type that function in. So it's 0.4 square root of t cosine of 0.06t dt. Oh, my settings are wrong. Let's go, I'm going to go home real quick and go to settings, general. I need to have this set in radians. We'll make sure before the AP test that all of these settings are set correctly. Let's go back here and do this again. So if I press enter, there we go. Okay, so then this would be the final temperature after those 5 minutes. So 73.043. I come back over here, zoom this. Alright, so I'm going to get 73.043 degrees Fahrenheit. All right. Be sure that you're going to at least 3 decimal places on these. That's the minimum number of decimal places you have to show for your answers on the AP test. All right, so we're under 15 minutes, and that includes explanation and technology issues and all that kind of stuff. So really not too tricky of a problem. In the packet of free response questions that I gave you, the other ones that would be similar to this one that you can go back and try to do on your own as practice would be on the 2011 test. It was number 2, so still on the calculator portion in 2011. On the 2010 test, it was number 2. So still in the calculator portion there also. On the 2009 test, it was number 5, so that's the non-calculator portion. It's actually kind of a boring question that year. They didn't try to give it any like real-world application at all. In 2008, it was number 2, so the calculator portion again. So those are the ones where you are reasoning from tabular data or working with information that's presented in a table. And so I would go through now and work as much as you can on those 4, and if you have questions about any of them, come and see me.